Everyone, and we'll get started. So welcome to the Energy Symposium sponsored by the Energy Institute here at the University of Texas. There will not be a lecture next week, which is spring break. There'll be one the following week after that on March 28th, which is Carla Lacerda, who is from ExxonMobil based in Brazil. So we'll get an international flair and talk 2 weeks from now. And today we have me, your normal host, Carey King, giving a talk. And the talk here is going to kind of be a fire hose of ideas, but there's a lot of ideas I think that are good to think about in terms of high-level macroeconomic modeling and how macroeconomic modeling should and in many ways does not consider the fundamental role of natural resources and in particular energy. So I'm going to go over a lot of high-level ideas. And it could go a tad longer than normal because I'm trying to throw so many in, but we'll just get started right away. So to get you in the mood for thinking about this, some of you may have gone through this kind of exercise before, but the idea here, this is a reverse color image Texas flag. Since we're here in Texas, some people show the American flag, but stare at the white cross in the center and try not to let your eyes move around while you're staring at the white cross in the center, and we'll just keep staring at it here for a little bit and try to make sure your eyes don't move around. And hopefully you've been staring at it for 10 or 15 seconds, and then when I move it away, if you're not colorblind, you should see the image of the blue bar on the left with the white star and the image of the red stripe on the bottom. That is the proper color image Texas flag. Now, I took this from listening to a lecture by Daniel Dennett. If anyone has paid attention to Daniel Dennett, he's a philosopher and thinks about consciousness and reasoning and free will and these kinds of things. And he goes through this exercise and he basically said something quite interesting, right? You are experiencing a red stripe. When I take away the reverse color image of the Texas flag, you are experiencing a red stripe, say at the bottom, but there does not exist a red stripe that you're experiencing, right? It's actually not there. Your brain has created this image in its own head, but there's actually nothing physically there reflecting the color red to you. And so when we think about economics, this is largely a similar idea. We all experience an economy. You're experiencing an economy, but there's not one economy that everybody experiences. So we get conflicting interpretations of what we think someone thinks the economy is. And so because there are multiple people, there are many of us, and we all experience economic activity in some way. I buy a candy bar, I buy a car, I rent a house, and I work for a living and earn a salary. Everybody's doing this a little bit differently, so there's different experiences people have. And when we try to describe something like the macroeconomy, the entire economy of the United States, for example, or the globe, everyone's experience is influencing their interpretation of that and their knowledge. So this means that economic theory is extremely important for explaining what's going on in the world. Theory is essentially what we use in science or in economics to translate what is happening in the world to what we think is happening in the world, or what we think causes what is happening in the world. And we can think about whatever the word cause means as well if you want to get really philosophical. So essentially I showed you this, a reverse color image Texas flag, and you constructed this in your head. And people studying the brain come up with a theory of why you would see one thing and then take it away and imagine something else in your brain. Similarly, in the world, we can measure certain things. A barrel of oil, actually in units of volume. It's a unit of volume. It's not really a unit of energy. We can measure kilowatt hours, which is charge moving back and forth. We have this definition of charge. We can measure people, machines, and even things outside of the Earth like planets, stars, and galaxies. So these are things we can measure. But what we construct for our society or construct ideas in our head like GDP or gross domestic product, it's not something out there to be found. It's an idea we constructed. For a useful concept. Energy, the concept itself, is not a thing. It's an idea that we came up with, and by positing this idea, it has proved useful to design machinery and understand how the world and physics work. We can construct ideas of value, social equity, policies, and regulations. So these are all things we construct in our head to try to explain things that go on in the real world that we can actually count, that are physical things. And so some of you may have seen a shorthand version of this quote before. All models are approximations. Essentially, all models are wrong, but some are useful. Usually it stops there. And however, the approximate nature of the model must always be kept in mind. So keep that in mind as I go through this. All models are wrong, but some are useful. And theory, in this sense, in science and economics is largely a mathematical model, right? So when I say theory, it's largely how can I translate things into mathematics. So your mother said you can do anything you put your mind to, and we developed laws of physics that say your mom lied to you. But that's maybe a little cruel on our mothers. They're not really intending to lie to us, perhaps. But our mothers wanted to inspire us. So your mom might have just wanted to inspire you. But the problem is that scientists have derived rules that describe the physical world, and some of these rules constrain the physical possibilities, and these rules have not been proven incorrect, and so our interpretation of the world must obey these constraints that we have determined to be true as far as we know. So let's just think about how that goes. So there are physical laws and resource constraints. These describe how we can and use and access energy. Energy drives and defines our economy. That's what this lecture is largely about, as we'll go through it. And when we take the economy, economics basically informs policy, largely speaking. When someone says analyze a policy, often what they mean is do some economic calculation and tell me what happens. And policy affects social outcomes. So we can have this line between energy, economics, policy, and social outcomes. And if we neglect any one of these, we're sort of missing the large scheme of things, and we're missing the big picture. But it doesn't just flow one way from left to right. There are feedbacks that go from right to left. So if there are certain social outcomes that we don't want or that we want to change, we might pose to change policy. We might choose to understand if our economic modeling is incorrect and isn't approximate enough, if it is not useful. And we might tend to think if energy or energy constraints are limiting our social outcomes as well. So any one of these things might feed back upon itself. And it's just sort of easy to imagine if you think long term, and don't just think about the last 100 years, but if you think of like the dawn of sort of the human civilization. If you're a hunter-gatherer society, these are largely based upon certain types of energy resources, hunting free-range animals and collecting fruit and nuts off of trees. And if you're doing this for your energy resource as a human, you'll have a certain arrangement of your society that's limited. If you go to agriculture and you figure out how to raise domestic crops, you can have an agrarian society, which you might invent concepts like private land, and you might have an army to protect this private land, which there was no concept before, the hunter-gatherer society. And then, of course, when you get to a fossil fuel energy society, you have a much larger energy surplus. Now you can do things besides just provide for food for people. Now you can start to build other things and allocate energy for all kinds of other machines and purposes, and we essentially get what we have today in our sort of modern industrial and global economy. And so now we're thinking about, well, what does it mean to go renewable or a low carbon or a zero carbon emissions economy? So something that hasn't been experienced in the history of essentially human civilization. Of course, the Green New Deal, and there's a lot of question marks here and a lot of arguments about what this would look like and not look like. And the point of this lecture is to think, well, what economic theories or physical theories do we have, and can they help us understand this at all, or do they actually mislead us in some ways? So the problem that I'll talk about, that we'll discuss in this lecture, is that most contemporary economic discussions and the sort of mainstream economic modeling essentially ignores energy in this feedback and input process. And by doing so, it does not provide a viable explanation for what it would mean to go low carbon or near 100% renewable energy. And I'll explain how this is. So instead of having, well, there are people working on viable theories and ideas, and we'll go over some of those. But we hear a lot of narratives of energy and economics, and what we want are theories or perhaps laws that we can trust and we think are true. So if I think about a narrative, this is just a standard definition you might find from looking on the web. The narrative is a story that connects and explains a carefully selected set of supposedly true events or experiences and intended to support a particular viewpoint or thesis. So if we break this down, we can have at the top a particular viewpoint or thesis, and for the purposes of this lecture, we can maybe say a theory about how things work as a structure or a worldview. Then there's a carefully selected set of events and experiences that are translated into a story. And we don't actually even need to use the word supposedly here most of the time. There's obviously a lot of talk about fake news and what's a fact and what's not a fact, but even if we take things and everybody agrees on what the numbers are and the facts are, the different worldviews or theories will end up using the same set of facts to tell a completely different story. So we don't even have to go to the fake news part here in this particular lecture. And so if these energy and economic narratives, we can think about them on two axes. We have an energy axis and an economic axis. And on extreme views of the energy axis, we might say there's fossil fuels on one side and renewable energy on the other. And you could pick up a book, a magazine article, or a newspaper article you could almost, in many cases, interchange fossil fuels with renewable energy for someone who's claiming that you can provide better social equity, higher economic growth, and a cleaner environment, right? Someone could argue this from fossil fuels, and there are books that do it, and someone could argue the exact same things come out of renewable energy, and that also exists, right? So we're trying to parse between these narratives. So on the economic axis, we will have extreme viewpoints of one, which I might call infinite substitutability or techno-optimism, in the sense that humans are very smart, and with increased ingenuity, we have technological solutions to our social problems, and this has happened again and again and again, and why would you think this cannot continue to occur? On the bottom, you would have the other viewpoint, which is the finite Earth viewpoint, or what I might call techno-realism. It says, yes, we're pretty smart, but we live on an Earth that is finite. It's not completely finite in its materials. There are asteroids and meteors that come into Earth, and we send satellites out into space, and sometimes people, and send them back so far. So there's a little bit of material exchange, and of course sunlight comes in the Earth, but from the broad perspective of a modern economy and the use of fossil fuels, there are finite restrictions, and you have to deal with these. So these are kind of the competing perspectives. And if we want to understand disagreements along the energy axis, what I'm claiming is you can't really understand these without understanding the disagreements along the economic axis. So I'm sort of focusing this lecture more on the economic axis than the differences of energy systems, but more on the differences of economic viewpoints and frameworks, and how this doesn't really help us traditionally understand differences in the energy axis. So I'm going to take a quote here from Martin Weitzman, who commented on a paper by now Nobel laureate Bill Nordhaus, who just won the Nobel Prize for Economics last year. And this paper of Bill Nordhaus, he was essentially criticizing the discussion in this book, Beyond the Limits, from 1992. And his paper here is called Lethal Model 2, or the number 2, because this is the second version of a book from 1972 called The Limits to Growth, which was essentially one of the first books to take a whole systems viewpoint of how essentially the world operates. How does population connect to natural resources, connect to industrial capital investment, connect to pollution, and how do all these things feed back upon each other? And so it's called The Limits to Growth because they assume that the Earth is finite, and that's a framework they put into the model, and when you assume the Earth is finite, you're going to have limited growth, and so the book is Limits to Growth. And so Nordhaus essentially criticized this book and said the methods were completely nonsensical. But there's a high number of people, including myself, that does not agree with Nordhaus on this, at least in 1992. I don't know how he thinks about it now. And here we have a book by Ugo Bardi that's The Limits to Growth Revisited Again. It's the same exact title as Nordhaus's paper in 2011, essentially explaining how Nordhaus didn't understand how the mathematical model actually worked, and how his criticisms were unfounded. So Weitzman's commenting in this paper, and he's comparing these two different worldviews, what he's calling the worldview of the ecologist and the worldview of the economist. So for the ecologist, sees everywhere that carrying capacity is a genuine limit to growth. Every empirical study, formal or informal, confirms this truth, and every meaningful theoretical model has this structure built in, right? I've got a theory, I've got a structure, this is what I assume is governing how ecosystems work. And so there may be temporary population upswings or even population explosions, but they always swing down or crash in the end because finite limits are imposing a carrying capacity on the system. And Homo sapiens is just another species, right? So yes, I know we're smart, I know we're clever, that's why we're called Homo sapiens, but we're still exposed to these carrying capacity constraints and limits to growth. So then he goes to the average contemporary economist, does not readily see any long-term carrying capacity constraints for human beings. The historical record is full of past hurdles to growth that were overcome by substitution and technological progress. So the numbers on contemporary growth and the evidence before one's eyes do not seem to be sending signals that we are running out of substitution possibilities or inventions that enhance productivity. So the economist looks and says, yes, that was a problem once before, but we invented something and it's no longer a problem. We've gone on to the next problem and we're going to solve that too. So we have these two kind of different perspectives. We have our cute little scientist with his beaker trying to understand population, using words like limits of growth, population, species, carrying capacity. That's kind of what an ecologist might look at. Economists maybe using a different set of vocabulary, substitution, hurdle to growth, not a limit to growth, technological progress and productivity. And so energy is largely a concept that you can use to translate between these multiple worlds, because living creatures require energy to survive, and physical capital in the world, like our cars and our homes and our buildings, use energy as an input in order to function in the way that they're designed to function. So energy is a translating concept that we'll discuss. So you can have these narratives about what the best worldview is or what a proper worldview is. You don't have to pick one or the other. And these worldviews and narratives are used to translate data. And trying to explain data is often trying to explain why past events occur, why do certain events happen, or how can I explain the data, but also why did things that didn't happen not happen? So you can just say, well, here's something that didn't happen, and I can explain why it didn't happen, and it can be convincing someone that you're right. So here's a quote from Lance Taylor on counterfactuals. So economists want to go beyond mere observation and ask counterfactual questions about how one variable relates to another. And it's precisely because they're counterfactual that these thought experiments are irrefutable, right? So it's maybe like predicting the winner of the Super Bowl or the World Cup. You can talk about it a lot beforehand, but if you're wrong about who's going to win, it doesn't really matter. However, when one variable causes the other in the algebraic sense, or like mathematical sense, if you try to come up with an equation that explains how one thing relates to another, this is a query the data themselves can't answer. It's just a bunch of numbers in a spreadsheet, if you will. So this is the major reason why macroeconomics is so theory-driven, right? If you want to explain trends in data that are just a bunch of numbers in a spreadsheet, you have to have some idea about why the numbers are constrained in a certain way. And in physics and engineering, we look at physical principles and try to use ideas like the second and first law of thermodynamics. And macroeconomics, you have to do similar things. You have to have ideas about what's constraining. So here's some data that you might think about adding counterfactuals to. This is energy consumption in the United States. It's energy consumption per person. And as I ask in my class, I show up a chart of squiggly lines all the time and say, is there anything obviously interesting about this that you might want to explore? And I would say, well, in this particular case, yes. There's a roughly 4% exponential growth from World War II until 1973 in the energy consumption per person, so you're growing at a rapid rate. And then after 1973, something happens. And in the early 70s, several things happen that I won't go over here in detail. But the data here are clearly different. There's a constant energy consumption per person after 1973 for the next 3 or 4 decades. And before that, it was growing rapidly. What happened? Who's got a theory for explaining this? And so you might see someone give a presentation that says, well, if those events in early 1970s didn't happen, that we would have gone up like this, and we haven't totally collapsed the world, and we're not totally sad, and things are still okay, so we don't really need all that energy consumption, and we did that by choice. And so they could say, here's this energy consumption that didn't exist, but the problem is this consumption didn't exist. It's not there. It's a counterfactual. It's a made-up story. This thing didn't occur at all. So if someone has a story about how you didn't need to consume that much energy, and you look at the data and you say we didn't, and you say, well, you have to understand their theory and their reasoning about why the red line might have been something to even think about. And who has time for that? I could draw a green line and say it was going to continue to go up exponentially. I could have a yellow line and say, no, I think it was going to do this if none of those things happened in 1973. But each one of these has to have some justification. What I can say roughly about this, or what I feel about this general trend, just to give you a feel, is from a system dynamics perspective, or the same perspective that would have been expressed, say, in the Limits to Growth book. If a system is growing exponentially, it's essentially far from any carrying capacity limit. Or it doesn't recognize that there is a limit and just goes up right against it, right? This is what you can sort of assume from an exponential growth. If people look at S-curves, or logistic curves of growth of technologies, the time when it's growing before it sees the saturation and the penetration of a technology basically looks exponential. And so in 1973, this exponential growth was over for the United States and largely for the world and OECD countries. And then afterwards, we were near some limit, or there was a perceived limit, and we reacted. Before 1973, there was no concept of end-use energy efficiency in the US, or at least the Western world. And after 1973, there was. For example, corporate average fuel economy standards or increasing miles per gallon standards for cars. Those came after 1973, not before 1973. So there was no predetermined plan to just get magically to 350 million BTUs per person per year and stop consuming energy at that rate. There was no plan for that in the United States. It was essentially imposed and we reacted to it. And so I'm sitting here thinking, well, energy seems to be a major explanation for changes in the 1970s. There's similar data in economic data that show that there were changes in the 1970s. And here's from just some statements from a standard macroeconomics textbook. And here's one at the top talking about the early, leading up to the 1970s. The period of high growth of output per worker. So output per worker here is like GDP per worker. So there's a high growth of GDP per worker until the mid-70s. And this was due to rapid technological progress. So this is in the textbook. And then number two, say, well, why was there slower growth afterwards? Well, the slowdown in growth of output per worker starting in the mid-1970s has come from a decrease in the rate of technological progress. So I showed you a chart of energy, and energy was going up fast before, and then it wasn't going up anymore. And I'm thinking, well, energy seems like it must be an explanation. And the textbook here is telling me technological progress. It kind of makes me feel like I'm a stormtrooper that has just been approached by Obi-Wan Kenobi, and he's got these explanations in the droid, and he's like, no, these are not the droids you're looking for. We could take that as like, no, energy resources, these are not the explanations you're looking for. There's nothing to see here. Don't pay attention. It's not a lack of energy. It was a lack of technological progress. And I'm a stormtrooper, and I'm going, well, is this a Jedi economic mind trick? What am I supposed to think here? I'm a smart stormtrooper. I've been to engineering school. And I'm pretty sure that the economy is about doing stuff, and I know that doing stuff and making stuff requires energy, because that's what I had to study when I was in engineering school. But what do you even mean by technological progress? And so now I'm going to give you a crash course theory in what an economist means when they say technological progress. And this will flash up this equation with different shapes over and over again here, but we'll get through it quickly. So in a standard textbook, you might see that there's an equation that would say GDP, or economic output, is some function of three things, perhaps generically three things: capital, K, how many machines and stuff do we have in the world, or some metric of that, buildings; labor, how many people are working; and resources. You might say, oh, well, great, I believe in thinking about resources, including energy, so natural resources and energy. And the next step is to throw away the resources. Okay? All right, so now we're left with capital and labor. Instead of just generically having an equation of capital and labor, we'll put in a specific equation, and this is essentially called the Solow-Swan growth model. Robert Solow received the Nobel Prize largely for coming up with this concepts behind this equation. And so we have this capital and this labor, and the capital is raised to some power alpha, and the labor is raised to 1 minus this power. And there's another term here that we have to account for that we'll explain here shortly. Instead of thinking about what this power is, we'll look at the economic data, and informs us that the power for capital should be about 0.3, and the power for labor should be about 0.7. What this represents is that people that work for a living get about 70% of GDP in their salaries and wages, and people that own capital and factories and apartments and such get maybe 30% of all the GDP going to them. And so we have these factors, and we roughly measure capital, we roughly have an idea to measure labor, and we have ideas from the data that inform us what these exponents are, and we have an accounting framework for GDP, and we survey people and we come up with this. So those are all things that we sort of measure in some sense in the real world, so we're going to throw everything we measure, or at least approximate in the world, on the left, and everything we don't measure on the right. And the thing that we don't measure on the right is called total factor productivity. And which, mathematically speaking, it's called a residual, or what's left over. So it's the things that your mathematical equation doesn't describe. And you say, well, okay, then we'll see how big that is and how important that is. And if you want to know how much it's changing, how much is GDP changing, how much is capital changing, how much is labor changing, so we're measuring these things, we can figure out how much total factor productivity is changing. Or we can figure out how much is it going up or down, the thing that we don't know how to describe, or that we haven't put into the model. And so this is largely what economists mean by technological progress. They're basically saying, well, it's everything I didn't put into this equation. It's everything I didn't assume is a piece of capital or labor I'm going to call it technological progress. Well, that's a large set of possible things that it could be. It turns out that this isn't trivial. This is about half of all economic growth in the United States of the last 100 years or 110 years. So we're using a growth model in a lot of cases that can't explain half of what economic growth is. And so you can ask yourself, this is a theory, it's an approximation, and is it useful? Now, it turns out that it's not that useful. Total factor productivity as technology, or at least the concept of technology, doesn't really equal anything meaningful. And I put these papers up here that you can view on the, at least look up on the video later if you're interested. But effectively, total factor productivity is a tautology. It's an identity. And another way of saying that is it's defined by the assumptions within the neoclassical growth theory, within this growth theory itself. If you don't have the neoclassical growth theory, you don't have the same concept of total factor productivity. And in fact, you may not even have to talk about it. So, in our economic narrative sense, we have a theory, which is that GDP can be represented by this equation. We have a set of supposedly true events or experiences. We have this measurement of capital that we claim is a measurement of capital. We have a measure of labor that we claim is a measure of labor. And we claim we can determine what these exponents in the equation need to be from the economic data. And we turn up with a story that total factor productivity is technology, and we want technological growth, and that's a driver and engine of, well, essentially a driver of economic growth, but without actually saying what it is. So, WWASD, what would a scientist do? What are some other options if we want to look at sort of physical sciences? And I'm going to throw some at you that are, I think, highly informative and useful to think about. So one is networks. Basically the concept of distributing something, mass. People think of information networks and social networks, but I'm going to be focusing on physical networks, things that move physical things from one place to another. They're like oil through pipelines or electrons through the electric grid, for example. So this is a way to think about energy systems across different concepts. And one of the longest sort of running network concepts, at least it wasn't thought of a network concept until recently, is understanding metabolism or energy consumption of animals. And so this metabolism is represented by the B here, and the M here is represented as the mass of the animal. And what this is saying is that metabolism does not scale with mass to the 1 power. So if I have a 10 times more massive animal, I don't have 10 times more metabolism, or the animal doesn't have to eat 10 times as much food. So I have an elephant here, which has a high mass, and a mouse all the way over here. These are about 100,000 times different in mass, but they did not have nearly 100,000 times different energy consumption. And so when the biologists were plotting these data, they were trying to figure out, why does this happen? I measure what's going on in the world, I measure how much animals are eating, and what's happening. And so the red line is if they were linear. So the red line is if a 10 times bigger animal would need 10 times more food. But that doesn't happen. The data do not fall along the red line. The data fall along this green line. And it falls along across from, all the way from a mouse to an elephant to a whale. And so this was puzzling to people. And it wasn't until maybe 50, 60 years later that a group of scientists trying to think about this in a sort of multidisciplinary framework figured out a rationale for why this is the case. And they largely used the concept of networks to do it. So the derivation of understanding this, what they would call 3/4 power scaling law, derives from thinking about how your heart is the beginning for distributing blood throughout your entire body. And as your blood goes through the aorta, then it splits into 2 arteries, and then half the blood goes one way and half the blood goes the other way, and then that splits again into 4, and then that's split again into 8, and then those split again into 16. And as you go further and further down the line, if you think about this as a network, that's a branching network, they can derive that this 3/4 power scaling law has to do with the time it takes to deliver blood to all pieces of the body and minimizing the pumping energy of the heart. So this has an energetic concept to it. So the some of the same group of researchers, this is from a paper by Jim Brown at University of New Mexico, a biologist, looks at the data for countries of the world. And they say, well, that's interesting for animals, but what about human economies, which is a very complex thing. And you get a similar type of structure. So energy consumption of the world, total primary energy consumption scales to GDP with the 3/4 power. They have 0.76 here at the top, but effectively near 3/4 power. Now this is a little bit different. This is a flow, power, energy per year, and a flow of money, dollars per year, which in the other case, it's a flow of energy into an animal and a mass of an animal, which is a stock. So one's comparing a flow to a mass or a stock, and this one's comparing a flow to a flow. So it's a little bit different, but it's still kind of compelling that there might be something there. And this is essentially to be determined, but if you can posit that GDP is proportional to capital, like if I have more buildings and more factories, I can produce more GDP. 10 times more factories might potentially have 10 times more GDP. There's economic theory that supports that as well. Then I could have something like a flow proportional to a mass or a stock, like capital. And so this would be just like the metabolic scaling law of animals. If we take this is a similar plot as the similar data. So this is energy consumption of the world, the energy consumption rate of the world. This is just plotted out for you differently, and GDP. So this is the same plot as before in a different way. This is the global energy consumption and global world product. And if you do a little curve fit here with the power law, if we were trying to mimic this 3/4 power scaling law, it's essentially exactly what you get again, right? So energy here is proportional to GDP to the 0.73, just looking at standard data here, right? So this starts to look pretty compelling as an interesting avenue of pursuit to try to understand the relation between physical quantities, energy, flow, and metrics in the economy. One more note on networks, to try to think this, stay at the global level. This is summarizing work by Andrew Jarvis in the UK. And he thought about the whole economy as essentially a network of places that extract energy resources, like oil fields and wind farms, and they're fixed in the ground somewhere. They're in physical fixed locations. And there are places where we consume energy, like our houses and this building. And there's everything in between, including cars, including people. So if you get in a car and move around, you're part of the distribution network. You're not actually part of an end-use system, because if I go to a restaurant to eat, the point isn't that I got in a car and went to the restaurant. The point is to be at the restaurant at a fixed location and eat the food. So I either deliver the food to me or I deliver myself to the food, but there is a distribution aspect there. So he accounts for this, and he just says there are fixed things that extract resources, there are fixed places that consume the resources, and everything is distributing the resources from one place to the other. And if you do that, consider that, this is not the normal way people think about energy services. The total energy consumed at fixed points, like this building, is the total primary energy to 3/4 power. So again, you get this sort of strange 3/4 power scaling law, and it turns out he has justification for explaining why you would decarbonize the economy, because moving carbon around takes energy, and carbon has mass. And if you move mass around and take energy, you want to minimize energy if you want to grow the network. So a growing economy essentially facilitates the need to decarbonize simply due to reducing the energy associated with distribution itself. So that's a network concept. What about things that occur at the end use? Things that an engineer might think about. And so aside from what I said about Jarvis here, I'm going to consider a car an end use, because that's considered in the example here I'm going to show. So a car is a piece of capital. An economist might call it a piece of capital. An engineer might call it a car. But for a car to work and turn into something like transportation or be part of the distribution system, it needs fuel. It can't operate without fuel. This is sort of obvious to anyone that thinks about it. But when we think about economics, we have to actually include this principle in the theory, in our framework. Because if you have a car that has no fuel, it's a piece of art. Right? Anybody seen this in northern Texas? Yes, the Cadillac Ranch. And I'll steal a quote here from Steve Keen in the UK, that labor without energy is a corpse. Labor being people, energy being food. If you don't have food, you're dead. While capital without energy is a sculpture. So why would you have an economic framework that doesn't consider both of these fundamental principles? And I'll come back to some work I'm doing at the end in which I put these fundamental principles in the model. Like I take this completely to be true and I put it in the model. So if we take this idea that a car is a piece of capital that needs a fuel input, we can describe the car capital in this sense, or any piece of capital that uses energy by some efficiency. It takes fuel input and it converts it to some output that we can consider actually still in units of energy. So in the case of an internal combustion engine, it produces some mechanical drive that Robert Ayers calls useful work. If we put electricity into an electric motor, it does the same thing. It's a spinning, it does mechanical work. But we can think about this for heating buildings, cooling buildings, and other aspects of what we would call useful work. So think about the fuel that ends up at the end use times the efficiency of the end use device, including lighting. We can think about lights as well. And so if you do this, if you think about useful work is the end use energy times its efficiency, and you just plot this over time for the United States, which is what Robert Ayers did and Benjamin Moore, you get the red line here. This is useful work. It still has units of energy, so exajoules per year here, or flow rate of power, and this is over the entire 20th century. So that's the red line, goes up, and the white line is GDP. And what you get from this is essentially, if you look at the axes, the useful work is about 2 times GDP measured in these units, and it's about a constant factor. So if I just assume that GDP equals useful work divided by 1.9, I can almost describe the GDP of the economy. So if I know all the devices and how many devices I have that consume energy and how much they're being used, as well as the efficiency at which they're using them, I have a pretty darn good approximation for GDP. And I don't have any labor here. Aside from that, this change in useful work, so again, this is this idea, what's energy end use times efficiency. If I see how much this changes every year, how much does it change one year to the next, and I compare it to estimates of how people think about how total factor productivity changes from the neoclassical economic theory and how that changes from one year to the next, that's what this plot is here. And so the change in total factor productivity from one year to the next is the red line. The change in total factor, or the change in useful work from Robert Ayers and Benjamin Moore's work is the white line. The time series of the data don't line up because they're not for the same period of time. But they're essentially, from this chart, obviously highly correlated, right? Once you start at the 1950s when the data overlap, they follow each other quite well. So what this is saying is that useful work effectively is the technology within the growth of mainstream neoclassical economic theory. They took out resources, and if you put resources back in and think about how we use resources and why we use resources, you can essentially explain what their theory left out from the beginning. So we can think about the lack of biophysical principles in mainstream economics, which is all just neoclassical economics, and there are people trying to do other things, so that's not to say that everybody's there. But what are the implications for understanding something like climate change and energy policy or energy transition to renewables? Well, here I'll just use the example here of Bill Nordhaus's model, because he essentially won the Nobel Prize for coming up with this modeling framework here, the DICE, what he calls the DICE model, for being essentially perhaps the simplest, what is called integrated assessment models that have some model of the climate, some model of the economy, and discuss interaction between these two to understand climate damages, how much would climate damage GDP in the future, and therefore how much should you mitigate against climate change. But his model assumes this framework I've already gone over, this GDP equation. And effectively, since total factor productivity is not a part of the, well, it's not an quote-unquote endogenous part of the theory, you assume it just on the outset. And the standard way he does it is to assume it grows at 1.5% a year at the beginning of the century, and then maybe grows only 1% a year by the end of the century. And if you do that, you're going to be 300 or 400 times bigger by the end of several hundred times bigger by the end of the century. And so this is important because, say the Obama administration used this amongst other models to estimate the social cost of carbon. So you have to ask yourself, estimating the social cost of carbon based upon a theory that ignores the role of energy, whose job it is to explain how to transform the energy system. All right, so is this misleading, or can using these kinds of models be misleading? I'd say yes. So here's a quote from a blog in 2015. This was right after the 5th assessment report of the IPCC came out, and they had discussed their findings. And so here's a quote from Joe Rahm's blog. To be crystal clear, my position and what the literature and field experience make crystal clear is that solving climate, in which he's saying stabilizing at 2 degrees C, or like a 450 parts per million climate stabilization level, is by any plausible definition of the word cheap. Indeed, it is super cheap, right? If you think it's cheap. So the IPCC reviewed the entire literature on the subject and concluded that the annual growth to preserve a livable climate is, the annual growth loss to preserve a livable climate is 0.06%. So what this means is, if you're talking about an annual growth rate of, say, 2.24% annual growth throughout the century instead of 2.30% annual growth in GDP over the century. And this would be to save billions of people from needless suffering. So if this is indeed the truth, it sounds pretty cheap, right? And so what he's essentially saying, right, the IPCC concluded that the annual growth loss to essentially mitigate climate change fully is 0.06%. But the literature did not conclude this. As I've showed, the literature and the economic theory of the models inside the literature assumed it from the outset. They didn't conclude that this is what the loss of growth is. The theory, the structure of the theory assumes it. Or at least it's not able to actually understand the feedbacks associated with how the energy system reacts with the rest of the economy. And so this is the model we usually have. Energy and policy and social outcomes. Energy is neglected. And so we have the model here that informs most of the IPCC. It's not a function of energy. And say if we have a policy to achieve zero carbon emissions, the social outcome is that there's no trade-off. There's no negative feedback associated from the energy system. There's, in some sense, maybe nothing to see here, move full steam ahead. And the question is, why doesn't that happen? So the modeling we need is energy is a function of, or the economy is a function of energy. The policy to achieve zero carbon emissions, if we have that same policy, we need to understand if there's trade-offs between things that we might need to achieve, like GDP or wage equality and all these other kinds of social outcomes. So, are there any data supporting that there might be social trade-offs? Yes, there are. So this is energy spending, the money spent on energy divided by GDP in the United States. So this is all money spent on like gasoline, electricity at the homes, and natural gas, these kinds of things. And so it spikes up here in 1973 and again in 1979 due to the oil issues, and then has a high mark there in 2008. The most major recessions are associated with the high points in spending on energy. So you can have a recession where energy is otherwise cheap, but the most dramatic ones were when energy spending was relatively high as a percentage. So we can think, well, other research shows that this tends to be the case. There's not a lot of data points here, but when energy spending is relatively high, say greater than 9 or 10%, on the end use, this tends to be associated with the major recessions. And so I'll tell you, that's the US data. This is the same concept for the world. There's spending on natural gas, spending on coal, and spending on electricity from things derived other from coal, oil, or natural gas. And so we have the same swings here. And then we can think, well, what if we wanted to charge ourselves for carbon emissions and internalize this in the economy? How much might that be? If I charge myself $10 a ton for CO2 and applied this to the carbon emissions from fossil fuels, burning fossil fuels, I would have some energy spending on energy plus the spending on CO2. If I charge myself $50 a ton, I'd have some other number. If I charge myself $100 a ton, I'd have some other number. And so we think, well, there was a major recession associated with 2008, and there were major economic turmoils associated with the late 1970s and early 1980s. These were times of high spending, and if you have this kind of turmoil, would you have charged yourself a lot for carbon or not? If energy is cheap, maybe you would charge yourself a lot, or at least you have the potential capability of charging yourself a lot for climate mitigation, but only in the times when energy is cheap. And so we can think about the future. How much do we want to reinvest or transform the energy system going into the future? Invest in low carbon, renewable things, nuclear, renewable, and storage technologies. But the faster you do it, there are implications because of sort of natural feedbacks and timing. So here's a way to think about this. The faster I invest in the rate of an energy transition, the higher the fraction of the economy is involved in the energy sector, because more people are getting paid to work in the energy sector, more people are installing things, more people are maybe doing energy efficiency in homes. And I need energy for that, and I need stuff. I need raw materials. So more things are getting allocated to that effort. And if that is occurring, then there's a higher fraction of spending on energy by the economy because I'm paying these people to do it, so I'm allocating these resources to it in the interim or the short term. And it could be a high enough cost share or a high enough shift to cause a high enough cost share of energy or energy spending as a percentage of GDP that you could put the economy into recession, because the data indicate if we go high enough that the economy is in recession. And so you could choose to spend yourselves into recession during a fast energy transition if you wanted to, but does anybody want to? Or would you choose to do this voluntarily. Now, the catch is that no one's telling you, except perhaps myself, that this is actually probably something that would happen. Most of the time, people think this is not even a choice they have to make, and so they don't think about it at all, and that's because the papers they read are based upon a theory that says that this can't happen. They're based upon a theory where you can still put energy into this equation, right? You can still take this equation and put another input, energy, into it, but they will say, in this case, the energy is raised to a factor of 0.06, which basically means 0.06 is a small factor, which essentially means that energy is not important to the growth of the economy. And this 0.6 comes from just thinking, well, the percentage of GDP that we mostly spend on energy resources is somewhere around 0.06 or 0.07 or 8. And if you change this from 0.06 to 0.08, the effect on GDP doesn't change very much. But the data indicate if we go from 0.06 to 0.08 or 0.09, that's the difference between growth and contraction. So the theory says you don't get a lot of difference in growth or contraction, but the data indicate that we do. Okay, so what if we actually consistently integrated concepts of biophysical and economic principles, which is what I've been working on, and all these other things have informed my thinking on this. So here's our energy consumption per person that we saw before, that I've showed you before. It goes up until the 1970s in the United States, then it goes roughly flat after the 1970s. And now I can show a black line, which is the wage share, which is what percentage of GDP goes to pay people wages and salaries, people that work for a living. It's roughly constant until the 1970s, and then after the early 1970s, it starts to go down. And it took probably 30 years of this trend before people really started talking about equality, and President Obama brought it up, and now, social equality is a large topic, but this trend, when somebody says this has been happening for 4 decades, it's because they look at this chart and say wages have been declining as a share of GDP for 4 decades. So the takeaway from here is that energy consumption per person went up and then went flat. Wage share was flat and then went down. And the turning point in each of them is right at the same time, at the early 1970s. And so you got to ask yourself, maybe there's something here. So I've been working on a model that essentially is in the framework of the original limits to growth sort of concept, but it's specifically geared to think about concepts like wages and debt and how money flows in the economy in a more modern sense. And so there are resources in the environment. Imagine that you're extracting resources and you got to do 4 things with them. One thing you do is you consume resources like energy, and you put it into capital that has to consume energy, like cars, or let's say a drilling rig in this case. And the drilling rig, or the capital that extracts resources, its job is to extract resources. So this is like using diesel to run a drilling rig that drills for oil, pulls oil out of the ground, sends it to a refinery, turns it into diesel, and then runs the drilling rig again, right? So this is a real cycle in the world, and this represents the energy feedback, or the feedback of the energy system to the larger economy. Energy requires energy to extract. It requires an energy input. So there's other kinds of capital that makes other things, including machines. So there's let's say this is factories that make machines, and they require energy to operate too. The factory needs to run on coal and electricity or some sort of fuels. And there's also natural resources embodied in capital, which is to say that the chairs you're sitting on are made of mass, and this mass originated in the environment. This clicker originated as oil or gas in the environment, and this is made of stuff. And so you have to account for that. So some of the physical stuff you extract turns into other physical things that we use. And then whatever's left over goes to consumption for us at our homes, for example. This would be like electricity consumption at your house or food consumption at your house conceptually. So if we take that framework and run economic models, and we're thinking about this data I showed you before, essentially I can get a very similar outcome. This is resource extraction per person, the same concept as energy consumption per person. That's the red line. It goes up and then goes flat after a while. And the black line is the wage share, how much wages is getting paid to people as a percentage of all the GDP. It's roughly flat and then declines. So they both have an up and flat trajectory in the red, and they both have a roughly flat and down trajectory in the black. Not only that, the reason that they transition at the exact same point, the reason that the wage share declines is because you've met a resource constraint in energy. That's actually the trigger for why the wage share starts to decline, because now something's got to give. I have to sort of make some allocation choice that I didn't have to make before when the whole system was growing. And so this is the takeaways on this economic model. Consistently tracks physical and monetary flows, we've sort of reached this time period where we shouldn't be talking only about physical flows. We shouldn't only be talking about monetary flows. We have to be able to talk about them consistently with each other. It can show economic decisions, like how much I invest in the energy system or invest in other capital, depends on physical resources and can affect social outcomes. And these sort of initial results provide a theory or a justification, or let's just say a theory or a basis for thinking about why trends in energy and money distribution might be related. For this case, energy consumption and wage distribution, or how much goes to wages versus capital versus paying debt payments as well, which is included. So it gives a physical basis for understanding the decline in wage share. So the takeaways in this whole talk, if you take away anything, energy is a necessary input for economic activity, and it can be a limiting factor. And macroeconomic modeling that ignores this principle is essentially not useful. So all models are approximations, and some are not useful. So if you want to talk about the long-term trends of the economy and you ignore the role of energy, it's, in my view, probably not useful. So we can and we must do better, and that's what I'm working on. I show up this eye chart full of papers that I have used to justify that I have taken information from in this presentation, so it's here for anyone who watches the video later to look at, and that's the end of the presentation, and we'll take any questions you have. Thank you.
Hi, Carey. I wanted to ask regarding that last graph where you showed how productivity per worker was declining, and then also energy consumption per, I don't know if it was worker or person, stagnated. So yeah, one explanation could be the one that you presented here today, but the other one could be that actually wages reflect, as in the neoclassical model, wages reflect productivity actually, and that it started falling, and that also caused consumption. So I guess how can you distinguish between what the neoclassical model, the story from the neoclassical model, which goes from decreasing productivity per worker to the stagnation of energy consumption, versus your your model that predicts the causation in the other direction?
Right. Good question. So I guess essentially the literature I look at in my line of thinking is to sort of think about what is productivity, and is the investment in one type of machine, how would you know if one investment is productive versus another? And from an energy standpoint, a productive machine is one that either extracts resources more cheaply or allows me to use them more efficiently. So that's the sort of useful work concept. I can produce more useful work in the economy by either making the end-use devices more efficient or delivering more fuel to them. And so anything that makes either one of those factors larger, in some sense, is productive. Now, and so that's a physical thing that we can count, and we sort of have energy principles for understanding why that would be the case. So I think that's a powerful argument. Another concept I thought about is why would we use the concept of energy efficiency at the end use anyway? Like, why didn't we use it before the 1970s? And we did afterwards. And my argument is there was no reason to do it. There was no energy constraint. It's like before the 1970s, we were not acting like an animal. The economy didn't have the constraints of like an animal's metabolism, but after the 1970s, we did. And if we have the constraints like animal metabolism after the 1970s, the reason why a larger animal consumes less energy per mass, or why its energy consumption scales with a 3/4 power of its mass, is because the rate at which all of its cells consume energy is actually slower than in a small animal. And so the translation to the economy is, if I want to have more houses, say that's more mass of the economy, more endpoints of consumption, which would be equivalent to cells in my body, each one of those houses has to get more efficient. Or that's actually not exactly correct. More generically, you would say each house has to consume energy at a slower rate. It could be because you got more efficient, or it could be because you just couldn't afford it. To the system, it doesn't matter. It just needs to not be having energy consumed at a slower rate at the endpoints. And it's exactly what you see if you look at housing data, that the residential energy consumption in the United States per household, you see until the 70s, each household was consuming energy at a higher, at an increasing rate, or we call a superlinear rate. And then after the 1970s, each house started consuming energy at a sublinear rate, or something that would be akin to the biological scaling law. So in my view, essentially the post-World War II to 1970s is an anomalous time. I think everybody recognizes that the data are anomalous to all the times before and after that. And it's a time when we just basically didn't have energy constraints. I think Robert Gordon's argument that there was a lot of investment in capital in the world during the World War II is a good one. And a lot of private companies got essentially free capital paid for by the government. And when you sort of double the amount of capital, you can do a lot of things, including extracting resources. You can do a lot of things cheaply.
I'm just curious about the causes of the decline. This first thing, the constancy, and then the decline of energy use per capita. We can attribute that to that boogeyman technological improvement. I mean, the energy intensity has come down in every developed economy along the line, and that makes per capita energy consumption come down on its own. We can do more with the same amount of energy than we could before. That doesn't seem to be a biological property. That's not true in the animal world, is it?
Trying to make a translation of GDP in the animal world. I don't know what.
No, you're saying that there's an analog in the biological world to what we've seen in the actual world. Decline. We've had energy use per capita hold steady and then decline a little bit at the end, right? An economist like me is a function of progress. We get more for 1 unit of energy.
Oh, right.
That's a decline in what we call energy. Biological processes that you're
Right. I think the
describing.
translation of a person to the cells in an animal's body is not exactly probably one-to-one. But a chart I could show, might have to shuffle through too many of the extra, is if you look at the energy intensity, which the normal way to think about energy intensity, right, primary energy divided by GDP, right, this has been declining since the early 1900s, but it wasn't always declining. It had a build-up before that. And so it's declining, and people that might want to project the future of GDP and energy might project a certain decline in energy intensity. And so you're essentially guessing, well, what might this decline be? And some people project the future by doing that. But if you use the useful work concept, it's essentially a constant. So if you had a choice between guessing the decline of something, that primary energy itself has multiple definitions, and what we put in GDP, well, I want to get into that. But if you had to project a decline in something versus just project something that has a relationship by a constant, which would you pick? And to me, I would pick the thing that's just related by a constant. So if GDP is equal a constant times useful work, I'll use that instead of projecting a decline rate of energy and relating that to GDP.
Of all the economic models out there that are considered valid and that are used, roughly what percentage do not consider energy?
Well, I don't know if that's a loaded question, as if I knew every economic model out there in the world, but I have had discussions with people about, say, the economic models that inform the IPCC reports. And as far as I can tell, they don't all have this neoclassical framework, and there are people developing others. There are some that use slight variations on this growth model, but that don't fundamentally address the idea of considering energy resources in the ways that I discussed here. So if I had to make a guess, it's over 90% and well over 90%. Yeah. I mean, essentially what people are taught in school. So what you're taught in school, you go apply in the world when you go to work.
Okay, so when you say energy per capita, different countries or different periods in the same country, so it's not the same energy, right? So for example, Qatar has high oil energy, so it uses, but maybe some other place Mexico has high food energy. So if we say Qatar is doing fine with energy, basically they need food from somewhere else. So when we say per capita energy across, I mean, I'm looking at the different types of energy. That's my first question. And second, so how do you address that with this model? And the second is you showed that per capita wages came down after 1973, whereas per capita energy in US stayed constant. During this period, what is the the profile of actual energy consumption, actual GDP, and actual population? Because what could happen is if population grew a lot more than the GDP, then the per capita wages could come down because there aren't so many jobs.
Right, so what I showed is not per capita wage, it was all wages paid to all people divided by GDP. The per capita wage would have been approximately constant during that time. So population did grow more slowly after the 70s. I don't know the exact rate, and now, at least for the, let's just say the United States or most Western European countries, of course, the natural replacement rate is below, or the natural rate of birth rate is below the natural replacement rate, and the population goes up because of immigration. So this is your first question. Oh yeah, the different types of energy. So,
Types of energy
Yeah,
has
yeah.
different limits.
all right. So, so the different types of energy is an interesting question on many levels. One is that not everyone counts total energy in the same way, right? The International Energy Agency counts primary energy in one way. The Energy Information Administration of the U.S. counts energy in another way. So this is another reason why the concept of useful work is actually useful, I think, in an understanding sense, is it's not paying attention to whatever we might want to call primary energy, like how do we translate 1 kilowatt hour of a wind turbine and equate that to burning a barrel of oil, right? You don't have to think about that. You just think about what ends up at the end use. How much energy ends up at the end point? So if I generate electricity from a hydropower facility or a wind turbine or a natural gas-fired power plant, I basically can neglect how I got the electricity, and I can just think about it was electricity and it showed up at my motor in my air conditioner at my house. And I just think about electricity. And I count the electricity because it's a thing I can count and it's unambiguous. I can count the work that comes out of my car engine, and that's also unambiguous. Or I can count the gasoline in the engine, and that's one way, and I can count the electricity in the electric motor, and that's another way. So that's another benefit of focusing on the quantifying energy at the end use rather than the beginning of the supply chain. Because at the beginning of the supply chain, there's inherent subjectivity. I don't know if that answers your question. So if Qatar, right, so Qatar is obviously, or Qatar is able to trade for food resources, as you say, with energy resources, and some people trade energy for food and vice versa. So that's, yeah, certainly allowed. Yep.
To clarify the animal metabolism, what you were trying to say is that we're in a society where we're consuming more energy, but with technological advances, we're kind of lowering our metabolism in order to...
You're lowering the metabolism, well, it's slightly more nuanced. You're lowering the metabolism per mass, if you will. So let's just say if the economy is 10 times as big, I don't need 10 times more energy to run it. That's essentially what's happening. I need a lower quantity of energy to run it. Yeah. So that's the metabolism analog. But the idea is that these things are fundamentally linked. So one other difference between animals and us is animals in some sense, well, depending on, I guess depending on the animal, if you think about eusocial species like ants or something like this working together as a colony, it may be more analogous to humans. But if I'm a I don't know, hunter-gatherer, I'm not creating the energy resources. I'm sort of finding them, and my investment to find the resources is me walking around or perhaps remembering where they are to go get them from season to season. But in our case, we're investing in end-use devices like cars and air conditioners and lights and homes, and we're investing in the thing to extract the resources to begin with. And when you think about the metabolism concept, it means that these two things have to work in tandem. The rate at which you invest in extracting has to be related to the rate at which you invest in consumption. And that's, to me, is the tie between the link after the 1970s. In order to actually afford to be able to extract more primary resources at a higher cost per unit based upon the previous resources, I had to make the end-use devices more efficient. Otherwise, it wouldn't have been affordable, and the energetic balance wouldn't have worked. So if I want a 100 mile per gallon car, or let's just say if I want to, whatever, $200 a barrel of oil or something like this, I have to start having cars that are much more efficient because the rate at which I'll be able to pull out energy related to how many cars there are is I'll have to be a much lower rate per car, I guess. So each car is going to have to consume less. So if I want higher cost energy, I need more efficient end use. So I think that's the linkage of how the network concept can help us think about that.
Thank you.
More?
Hi, really interesting talk. I had a question about the points about high energy spending when you're trying to do rapid transition. And it seems like in the 70s when the US was spending a lot on oil, then, you know, they were spending a lot of money out of the country. But if you were having a fast energy transition where your country on, you know, panels and car batteries and so on, then the effect on the economy might be a lot different, and where your jobs there instead of just sending money out of the country. So how do models like what you're trying to do, like try and capture the differences between?
All right. Investing in energy that is domestic versus investing in energy that is foreign or exported. So that's obviously an important concept, but we can think about it that way, or we can just think about it as the globe overall. So mostly I've been thinking about it as something generic like the globe overall. I guess one difference with the United States now, and oil in particular, or energy, is we're importing less oil now, but we're essentially not consuming more oil. Whereas in the 1970s, we were consuming more and more oil, and while we were importing more. So in some sense, if we're selling oil to others, it's in some sense because we can't afford to consume it ourselves. And so we have to think about that as well, right? Why would I be exporting oil and natural gas from the United States, the largest, most free economy in the world, if our citizens could afford to consume it? Maybe one of the reasons why we export it is because they can't afford to consume it. So that's a complicating factor. But for the whole idea of an energy transition, it is easiest to think about it as the entire globe, but it's also important to think about, you know, do we care if China's making all the solar panels and batteries and we're just importing them and we send all the money over there? The only reason we'd be able to afford it is because we have some other benefit in trade, essentially, or potentially a benefit in trade with everybody else in the world, so I guess it should work out. And we could think, is the reason why solar panels are cheap because they're made in China and the wages there are lower? Well, partly yes, but I think a lot of people look at this, say it's, you know, it's automated as well, and solar manufacturing and environmental constraints and or less environmental constraints in China as well. So these are all complicating factors, but I think the general trend would still hold, at least at the global level. If we actually did transition the whole energy system, we're going to have to make the things more efficient at the end use. So I think people talking about the Green New Deal, at least get that right, that you're going to have to get more efficient at the end use. But what we have to think about is how much investment is required to do that, and how that has to go in tandem with the investment in new extraction devices like wind turbines and solar panels. And so the whole idea is, you know, if 15% of the whole economy were involved in doing this energy transition because you wanted to do it so fast, you needed that many people, and you needed to convert factories over to doing that, like in World War II or something, you had to convert factories over to do that. This is essentially the antithesis of everything that's happened since the industrial transition. We used to spend a very high fraction of GDP on energy in an agrarian society, and fossil fuels and machines essentially have made that shrink to less than 10%. And so the faster you go in an energy transition, the more you're going back in this spending as a percentage of GDP, which dynamically should put you back in a lower growth state, closer to the agrarian society. So that's the hypothesis, and I'm hoping that my model can further develop, can provide some insight into that question, and that's pretty much why I made the model, to try to answer this question, but I'm not there yet. Okay, I think that's it. So thank you everyone for coming, and see you in a couple weeks.